I want to present a solution for the Iran Math Olympiad 2020 problem 5 from the second round. At first, let's have a look at the problem statement. We call a pair AB square makers if both A and B are integers and AB plus 1 is a perfect square. Now we are asked to find all n for which we can divide the set from 1 up to 2n into n pairs of square makers. Okay, at first let's write down the equation a times b plus 1 equals k squared. Here we can bring the 1 to the right hand side and get that ab is equal to k squared minus 1. And now we can factor the right hand side and get that this is equal to k plus 1 times k minus 1. So we know that if a and b have difference 2, then ab plus 1 must be a perfect square. This is really nice because now we can try to pair these numbers in the set such that in each pair the difference of the two numbers is equal to 2. So let's have a look what happens if n is large enough and we have all the small numbers to build pairs. Therefore our first pair could be 1, 3. Here we see 1 times 3 plus 1 is equal to 4, which is indeed a square. Then our second pair is we can choose 2 and take 4. Then we can take 5 and 7, and then we can take, for example, 6 and 8. Now we can directly see that if we have 4 adjacent numbers, for example here 1, 2, 3 and 4, we can make 2 pairs of them such that both of the pairs are square makers. Thus we see that if n is even, which means that we can write n equals to 2a, that we can divide our set here from 1 up to 4a into the square makers 1, 3, 2, 4, then 5, 7, 6, 8, and now we go on with the same idea, and in the end we have the two square makers 4a minus 3, 4a minus 1, and 4a minus 2, and 4a. So we know that if n is even, it is possible. Now our second case is that n is odd, and here we can write n equals 2a plus 1. Now if we have a look onto the set from 1 up to 2n, we can write this as the set from 1 up to 4a plus 2. Here we directly see that the biggest number in our set is congruent to 2 modulo 4. This means that we have more numbers congruent to 2 modulo 4 than numbers congruent to 0 modulo 4 in the set. And since we deal with perfect squares in our problem, we are motivated to consider the numbers modulo 4 in the set. So let's have a look onto a number k congruent to 2 modulo 4, and k should be in our set from 1 up to 4a plus 2. Okay, so now let's have a look on k times b plus 1 for some arbitrary integer b from the set here. The first case for b is that b is congruent to 1 modulo 2. Here we get that k times b plus 1 is congruent to 2 plus 1, which is congruent to 3 modulo 4. But this is impossible since 3 is no quadratic residue modulo 4. So let's have a look on the second case. This case is that b is congruent to 2 modulo 4. Here we get that k times b plus 1 is congruent to 2 times 2 is 0, plus 1 is congruent to 1 modulo 4. But this is not directly a contradiction, because 1 is indeed a quadratic residue modulo 4. But now, if we have a look on b and k, we see that 2 divides both b and k exactly 1 time. Therefore, we know that 2 divides the product k times b exactly 2 times. This means that k times b is congruent to 4 modulo 8. And from this, we get that k times b plus 1 is congruent to 5 modulo 8. But now 5 is no quadratic residue modulo 8, and therefore this case is also not possible. Therefore, our only possible case is our third case, namely that b is congruent to 0 mod 4. But now we remember that we found out that in our set here there are more numbers congruent to 2 modulo 4 than numbers congruent to 0 modulo 4, and therefore we can't pair each number congruent to 2 modulo 4 with a number congruent to 0 modulo 4, and therefore in the case that n is equal to 2a plus 1, which means that n is odd, we can't find a solution. And therefore we are done.